Why there are words on this presentation? This is because the cinematic approach that we are using is called swarm approach, swarm model. So we are using a model that is inspired by the natural swarm, bird swarm, ant swarm, and so on. We will see this. The main goal of our model, that now it's on its first steps, let's say in this way, is to be able to simulate material deformation in a quantitative way. Okay? We will discuss this in detail in a few slides. Let's see in some detail. So, a new model. What is this? Now we have 4 papers on this topic to say that we are introducing it and developing it in time. It is a 2D cinematic model. Cinematic means that we care only about position. We do not have force, we do not have stress, we do not have nothing, not energy, nothing. We care only about position. Okay? Cinematic. And it's 2D, but we can expand to 3D with details. We wrote the code in Python and use CUDA, that is a way to use the GPU. So we can use parallelization. That means that the algorithm does not evaluate the position of the points one at a time, but all the time in one shot. Okay? It's fast. It's a swarm system, as I have told you, and the goal is to make material deformation. Okay. Now, be really quick on this topic. We have already know. We said that we have introduced higher order model, generalized theory to describe complex material. Okay? So in this presentation we will focus on the first and second gradient. Okay? We will try to simulate these 2 kind of continua. 2 words on the most common way to simulate material deformation that almost all you use all day, I suppose. We have a continuum, we divided it in element, we evaluated the solution of the deformation inside of this element, we patched together the solution and made an interpolation, okay? And so we get the solution. It seems easy, it's not, but the main thing is this. When we have to handle the case when the continuum starts to break, start a fracture, or the geometry is complex, or we want to simulate a porous material with some characteristics, and so on. There are some cases in which this method is really slow, and so in this context we want to introduce a new model that completely avoid those problems and try to be fast where this model is slow. This is the incipit of our model. Okay? And we will see how. So, what is a model? It is a large group of locally interacting individuals with common goals. Locally, it's a keyword. That means that the elements of the swarm know only what happens around them. They do not know where they are in the swarm, or if they are inside or near the edge of the swarm. They only see their neighborhood or elements, the neighbors, and so they react as consequence. So let's be quick. The swarm approach is a part of the agent-based model. Maybe you are more familiar with the cellular automata. So if you imagine a continuous cellular automata, you can see the swarm approach like a particular case. Let's see the way. So the agent of the swarm, because it is the right word, agent, are uniquely identifiable individuals for the swarm that are characterized by attributes like, for example, the position in our cases, or the role in our case, and methods that are the behavior. So how it the element, the agent of the swarm, have to do when the situation around them is this. The configuration of the points, your neighbor are this, you have to do this. And another important thing is the behaviors, the change behaviors. Okay? So you know that you act in this way, but in this situation, you know that now on you have to behave in a different way. You will see that this is important. An example, very quick. Swarm model. Okay? So in the 80s, Reynolds simulated a swarm of birds in this case, in this way. The element of swarms are this object, this triangle, characterized by direction. So simply introducing a way to get the element near, a way to align the elements, and a way to avoid collision, got simulation plausible in 2D in this case, but he made in 3D for movement for swarm of birds. Okay, let's see now how we take this to material deformation. Now, our swarm is characterized by three things: the structure, either follower distribution, and points applicating algorithm. The structure. We use it for our swarm, not random points, but points on certain lattice, in particular center square lattice and hexagonal lattice. In this way, we have also the definition of neighborhoods and neighbors. So for the red point, first neighborhood, so first neighbors, and second neighbors. We consider only these two, okay, in our model at the moment. We have said that the points can have a role. There are two roles, leader and follower. You can be, the points can be a leader, that means that they lead the deformation, because they have an imposed a priori bias, let's say movement. So they take those points and they, step by step of the algorithm, move them, so they move. The follower instead adapt their position to the neighborhood, their neighbors. Okay? Maybe in their neighbors there are the leaders. So you move the leaders, and you see that the followers follow the leaders, and in let's say in a global perspective, you see the deformation. We do not have say to the point, you have to do this because you have to respect the Poisson ratio. You have to do this because we have applying a share, so you do have, no. We always say, these are the points you have to look. You have to look their position. You have these rules to decide if you have to go near or go far, and they have this output. Okay? It is called this, but also other things that we will see later, emergent phenomena, where you define something with simple rules locally that lead to complex behaviors in the global aspect of the model, in this case. So, I will say that we move the points. How? The algorithm that change the position of the followers is this. The position in the next iteration of the algorithm is the previous position plus a term that we call interaction. The interaction is not a force. I've told you we do not have force, we do not have velocity, we do not have elastic constants. Okay? We do not have physics, let's say in this way. Okay? So it is an interaction because in the language of swarm models, it's called in this way. Okay? Interaction, in this case, it is composed by two contributions, A and B. A is a contribution that is linear with the difference between the actual distance between 2 points, and then we want to evaluate the interaction of the point E. Okay? So we look at J, its neighbor, and how its distance, more or less of the distance that we had in the reference configuration, the initial configuration. Let's see in this way. If J is far, E has to get near. If J is already near, E has to go away. Simple. Okay? And is noted this parameter alpha. We will see later some important thing. Instead, beta is linked with the couples in the neighborhood. So let's say this is the neighborhood of the black point. So we can recognize three different opposite couples in this neighborhood: the green, the red, and the blue. Okay, for an hexagonal lattice. Okay, so these terms is linear with the distance between the point E, that is the point on which we want to evaluate the interaction, and the middle point of the chosen couple, in this case the green, in a deformed configuration. So there is this phase, and so E is far away. It has to get near this point. Okay? So, as you have seen, we do not have use force or say at the point that there is this physics rule that they have to follow. Okay? We have defined only just two simple rules. You can answer why you have chosen these two strange rules. There is a physical meaning. We can say that the first gradient is related with locality and linearity, at least on smaller deformations. And so it can be related with the contribution A that was linear with the distance compared with the reference distance. Okay? Instead, the second gradient can be related with the non-locality, because structures, edge effects, curvature. Okay? And so we thought that the interaction on higher order neighborhood, okay, so the neighbors that are far away, okay, can induct some non-local effect. Local in terms of position, of how much is near. Okay, non-local in the sense I told you before. Okay, when I told you about swirls. Instead, the contribution B is linked with the curvature, because try to get point aligned. Okay? We can introduce other contribution if you want, but let's be quick and to see some results. Okay, but I have two last warnings. The results are still quantitative. We will see what I mean, and the model lacks a concept like force, time, and energy. It's really important. So we have to be careful to interpret the result. If I show you the results of the algorithm like they came out, you could only see points. You see, okay, I see the global deformation, but I do not understand what it is. So we have invented a method to see also the local deformation. So we introduced these areas that we can recognize in the lattice, okay? Also for the center square. And we have colored the areas, okay? With a bar that represents the percentage variation of the area of that element in modular, so usually. Okay? So now you can see the global deformation and the local deformation. Okay? Why? You can say why this is related with the local deformation. This is because we can see that the energy can be related with the variation, local variation in continuum mechanics. Local variation of the area squared. Okay? And so this can be our version, or at least a quantity that is compatible to be our energy. It's not an energy. Okay? It's the thing that is near in our model. Okay? Important. So let's see some results. Now we have a traction test first gradient in our model, in the language I told you until now, okay? And 50% elongation. On the top we have hexagonal lattice, on the bottom center square lattice. You can see we used for a sample with a swarm with an hole and without hole. The important thing to say about this picture, these four simulations, are that we got the Poisson effect naturally. We do not have any problem with the hole. The presence of the hole for the argument is not a problem for us. Without and with the hole, it's not a problem. Okay, the model does not have a slowdown. We can see a compression test about 80%. It's important to note these blue spots that do not seem so blue here but are blue, that are the position where it should start to crack, the fracture, if we continue to do the compression test. Okay. We can also perform a flexion test with hole and without hole. We can perform shear test with hole, without hole, without problem. It's not a problem to do this test or the other one here before. We can do.
What are the colors? What do the colors represent?
The local variation of the area. We have colored the area of certain geometrical figure, and we can recognize in the structure. And so we colored the variation of those areas between the actual configuration and the reference configuration. So we have an idea of how it's compressed or dilated a region. Okay? Here we can see a second gradient test, about 50% elongation, always hexagonal and center square fractions. The main point is we can recognize some characteristic of the second gradient simulations compared with continuum mechanics in them. For example, the presence of edge effects, okay? The fact that our measure of local deformation is more distributed, it's more so this means that our algorithm could be faster, could be, I don't want to say better, but I could say competitive. Okay, competitive. So let's finish with a slide taken from the Lisola. Usually the Lisola show this side of the slide, where we have here a simulation done in console with 1 million of elements per layer. And this simulation, to do this simulation, it takes about 12 minutes. Okay? Because they reproduce the whole structure. Using instead the second gradient continuum mechanics, they simulate one continuum or second gradient and then reconstruct the structure. And in this way, they manage to obtain this simulation that is really detailed in about 20 minutes. A huge improvement. In our model, with all the precaution that I will say to you, okay? But this kind of simulation takes about 5 minutes. But we are using this model on a desktop PC, at least when we made this simulation, on a desktop PC. And our code is not optimized because we are not, let's say, informatics. Okay? So it's not really optimized. We wrote a code. It would be the most inefficient way to do this thing. Okay? But overall, this kind of simulation takes about 5 minutes. Sometimes 2 in the traction test, sometimes 5, 6, 7 in the shear test, because we wanted, for numerical reasons, go a bit slower in the share. Okay? So I avoid all the detail to give you an impression, let's say in this way. Maybe you did not understand something, because I know I avoided some important things to be quick, but overall, thank you for your attention.